Welcome to The Explainer. Today, we're diving into something pretty cool. How we can get our computer programs to stop just, following a basic to-do list and start actually making smart decisions all on their own.
All right, so let's get right into it. Think about this. The real magic of programming, it isn't just about telling a computer what to do step by step. No, the magic happens when you give your code the power to react, to choose its own path, to actually adapt based on the information it's getting.
And the way we do this is with something we call control statements. You can kind of think of them as forks in the road for your code. At some point, the program has to make a choice. Does it go left or does it go right? These statements are basically the traffic cops directing the whole show.
Okay, so let's start with the most fundamental choice of all. What if we just want our program to check one little thing and then decide what to do next?
So the most basic choice you can make is with a simple if statement. Like if this number is odd, let's multiply it by 2. Simple. Otherwise, we just move on. But here's a super important detail, especially in a language like C++. The computer doesn't really get true or false. For the computer, it's all about the numbers. Any number that isn't 0, that's true. Only plain old 0 counts as false. That's a huge concept to grasp.
But what if you have two totally different paths you could take? That's where if-else shines. It's literally the code version of saying, if the weather's good, I'll go for a walk, else I'm going to the movies. The program checks the condition and picks one path, and only one, never both. And this right here, this is a perfect example. Just look at this code. If the grade is 60 or higher, it prints pass, and then it's done. It completely ignores the else part. But if the grade is, say, 59, it skips the if block entirely and jumps straight to the else part, printing fail. It's a clean, simple, two-way street.
Okay, but life's rarely that simple, right? What happens when you have way more than just two options? Let's level up and tackle a classic programming challenge, assigning letter grades.
So, let's say the client gives us the rules. Over 90 gets an A, over 80 gets a B, and over 60 gets a C. Seems easy enough. Our first instinct might be to just write a separate if statement for each one. I mean, it seems perfectly logical, doesn't it?
But, we run a test with a grade of 95, and look what happens. It prints A, then it prints B, and then it prints C. That is definitely not right. You can't get 3 grades for one test.
So, what went wrong here? And this is where it gets really interesting, because the mistake wasn't the computer's, it was ours. See, a grade of 95 is greater than 90, check. But hey, it's also greater than 80, and it's also greater than 60. The computer isn't making one single choice here. It's just going down the list, checking each if one by one. And, well, it's doing exactly what we told it to do for each one that's true.
Okay, back to the drawing board. Let's get way more specific. We'll add range checks. For a B, we'll say the grade has to be greater than 80 and less than 90. That should box things in and fix it for sure.
So we test it again. An 85, it correctly gets a B. Awesome. But then it also says fail. We've fallen into another logic trap. The problem here is that the final else statement is only attached to the very last if. It has no idea about the other checks we did before it.
The real solution, the elegant solution, is to nest our choices. We build a chain. First, we check for an A. If that's not true, then and only then, inside that else, do we check for a B. If that's not true, then we check for a C. This creates this beautiful cascade of options where only one can ever be chosen. Once the code finds a true path, it runs it and skips the entire rest of the chain.
This brings up a really common myth in programming. You'll see else if written all over the place, and you'd swear it's its own special command. But it's not. It's actually a bit of an illusion. What the computer really sees is just an if statement tucked inside an else block. That's it. It's just a clever formatting trick that we humans came up with to make our code look cleaner and easier to follow.
Now that nested logic we just built, it works perfectly. But for this very specific job of checking one variable against a bunch of different constant values, there's actually a much cleaner, much tidier way to get it done.
Let's talk about the switch statement. I want you to imagine a big party hall. There are different doors, and each door is for a specific guest. But here's the weird part about this party hall. Once a guest goes through their door, they don't stop.
They just keep on walking right through into the next room and the next and the next. In programming, we call this fall through, and it can cause some real chaos.
So if we don't want our party guests crashing every single room, we've got to find a way to stop them once they've found their spot. We need to, well, build some walls.
And that wall is the break keyword. It's simple, but so powerful. As soon as the code hits a break, it immediately gets booted out of the entire switch block. So the big takeaway here is, unless you have a very specific reason for that fall-through behavior, you're going to want to put a break after almost every single case. It keeps everything neat and tidy.
Okay, so we've mastered making choices, but what if we need the code to do the same thing over and over and over again? Well, that's another type of control flow, and we handle that with loops.
Let's just touch on two key types here. Over on the left, we've got the while loop. This one's kind of cautious. It checks the condition before it does anything. So if the condition is false right from the start, the code inside might never run, not even once. But on the right, we have the do while loop. This one's a bit more eager. It's guaranteed to run at least once because it runs the code first and then checks the condition. This makes it absolutely perfect for things like user menus, where you always want to show the options at least one time.
All right, we've seen how code can make choices. But for our last point today, let's pull the curtain all the way back and look at what the computer is actually thinking about when it makes these decisions.
I mean, think about it. You press a key on your keyboard. You see a letter pop up on the screen. But what did you actually send to the computer's brain? What does it see?
Here's the mind-blowing truth. Computers don't understand letters, or symbols, or anything like that. They only speak one language: numbers. When you press a key, your keyboard sends a number code. Then, a universal decoder ring called ASCII tells the computer, hey, when you get the number 65, show the user an A. To the machine, it's all just numbers.
And that means that every single key you press, every symbol you see, is just another number being crunched behind the scenes. It really makes you wonder, doesn't it? What other secret numerical languages your computer's speaking right now just to make all of this possible?